Welcome to this video, produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on work energy and power, and in particular on potential energy. Mechanical energy due to position is known as potential energy. You can think of it as potential energy, that is, of energy stored in an object which gives it the potential to move when released. For example, if you hold a stone stationary in the air and then let go, the stone starts to move, and in so doing it releases potential energy. We'll see more what that means in a moment. The two main examples are gravitational potential energy, which I've just illustrated, and elastic potential energy, which arises when you have energy stored in a spring. So you hold a spring compressed, then let go, and immediately energy is released. Anything on the end of it will be catapulted away. In each case, the stone held and then dropped, or the spring compressed, you have the idea of energy which is potential when a situation is released. In this video, we're only going to consider gravitational potential energy. Elastic springs and strings come later. Now, all bodies with mass experience a gravitational pull. The force that acts upon them's weight, and it's proportional to mass. So it must be of the form mg, where g would therefore be a constant of proportionality, but it's what we call the acceleration due to gravity. G meters per second squared, to give it its full description, is the acceleration due to gravity. Well, why use a g? Because surely it's always the same. Well, we tend to take g as 9.8, which is an approximation. A better value is 9.81, sometimes just 10, according to how accurate you want to be. But there is a bigger question about whether g is actually constant. Yes, it is if our consideration of experiments is only in a relatively confined space. If that confined space were the top of Everest, you would notice some diminution in the value of g, because gravity diminishes as you go up from the face of the Earth. So a more refined model would involve g having some degree of change in it over the particle's path, but that's really only necessary for problems concerning space rockets, where you've got large distances and large velocities. So for our purposes, g is constant, and we normally take it as 9.8. You'll see that it's often written as g equals 9.8 meters per second squared, which is a bit inconsistent because g, strictly speaking, should be a number, but it's usually written like that, and it's clear enough what it means. Now, if an object moves in a vertical direction, then it'll either get faster because it's coming down, like a stone dropped, or it will need an effort from some other agency to push it upwards. Or it'll need some kinetic energy so that it's already travelling upwards. Now, these are situations which we aim to analyse by using potential energy. Now, potential energy is always concerned with work done against gravity. Why against? Because potential energy is created whenever you work against gravity, that is, you move upwards, and it's released whenever you move downwards. In that case, you have the potential for gravity to do work. Now, either way, the general expression used is mgh, and it's easy to see why that's justified in the case of something moving vertically, because it's simply the force mg and the distance moved, which is h, whether it be up or down, with the appropriate sign. But what happens if you move obliquely? Let's consider here a force system where you've got a weight system acting on a particle which is moving up a slope. Now, what does work do under those circumstances? Well, because work done depends on having the component of the force in the direction of movement, we would have to resolve the mg to get mg sine alpha in the usual way. And the distance, if we're rising a height h, by doing a trig analysis on this triangle, sine alpha is equal to h over ab. We can soon see that ab is h over sine alpha. So the force component times the distance moved gives us that expression, and lo and behold, the sine alpha cancels out. So you end up with mgh. Interesting that, because that's what I got when I considered the particle moving vertically, or body moving vertically. And indeed this is an important result, that if you consider work done against weight or work done by weight, in both cases it depends only in the height gained or lost. Hence the general expression for potential energy is mgh. There's a slight confusion here about whether I mean an absolute value or a gain. Well, it doesn't really matter, because in any question of potential energy, it's usually a matter of taking the original position as the zero of potential energy, and then if you move up, potential energy increases, and if you move down, it decreases and becomes negative. The important thing to realize is that if you move up, energy is increased, and if you move down, energy is released. So, to summarize that result once more, the work done for or against gravity depends only on the height gained and not on the route. And for that reason, gravity is known as a conservative force, and it means, in fact, that if you move in the opposite direction, not necessarily by the same route, but if you lose height having just gained it, the same work done that you did to create the potential energy is then realizable as work done to create kinetic energy, perhaps, or some other form of dissipation as it comes back again. So gravity is a conservative force because which means two things: it has a potential energy function, and it means also that it doesn't matter what the route is if you're considering the work done. So, if an object is moved from the surface of the Earth to a height h, taking the surface of the Earth as our zero, then the work done against gravity will be mgh, and we say its gravitational potential energy is mgh. When you move up, energy increases. You have to do work against gravity. When you move down, energy is released, and gravity does work for you. And that stored energy in the potential has the creative capacity to make kinetic energy when you let the object go. Now here's a standard example of this. If you have a hydroelectric scheme, you have water stationary at a great height, and then you release it, and as it travels downwards it gains velocity. The sluice gate is open, the water rushes down, and it's piped to drive a turbine. The water now has motion and hence kinetic energy, so the potential energy is realized as kinetic energy. Now let's look at a simple case here which does no more than apply the principles. We've got a mass 30 grams. Thanks, you must convert that to standard units. So on the diagram it appears as 0.03. There you are, that's the mass, and this is the weight. It's on a slope and it's being pushed up it, so there must be a force to push it up. There will be perhaps resistance forces, there'll be a reaction from the plane. Now what we're interested in here is the gain in potential energy, which is essentially the work done against gravity. And our calculations on the previous slides have shown that we're interested in finding the height. So if the slope is 2 meters, let's draw a quick model of the slope. The slope length is 2 meters and the angle is 60 degrees, then we're talking about a height which will be 2 times the sine of 60. So the h in the figure there is equal to 2 times the sine of 60. Now if you know your stuff, sine 60 is root 3 over 2. So that's 2 times root 3 over 2, and hence is just root 3. So the height gained is root 3. That calculation is summarized on the next slide. So here we have the root 3, which gives us the height. Now from this we can say that the gain, the gravitational PE gain, so that's a gain, is going to equal the mass 0.03 times gravity, which we normally take as 9.8, times the height, which is root 3. Well, that shrieks for a calculator, so let's do the calculation, and there we have on the next slide, there we have the calculation 0.03 times 9.8 times root 3, and we've taken their G as 9.8, of course, and that works out from the calculator as 0.50922. I've put the dots in to indicate that that was what was showing on my calculator display, and then on the next line I've rounded it. So the gain in potential energy, remember I said you go up, you get a gain in potential energy, and you do work against gravity. That gain is 0.509 joules. Now let's consider something coming down. It's a stone which is held stationary 10 meters up and then released. Are we to find the change in gravitational potential energy? Well, in this case the change will be a loss because the body is moving downwards. So what will that loss be? It will just be 5g times 10, that's the mg times m times g times the height, and we'll take g as 9.8. So that will give us the change in gravitational potential energy, and it will be a loss. If you like, or to concur with what I said before, in this case gravity is doing work for you, and that's what gives the body its speed when it hits the ground. So we take the gravitational potential energy, it will be a loss, hence the minus sign, and so the change in gravitational potential energy when we've put that through the calculator is just 490 joules. Now the next part is to ask the kinetic energy at the instant it hits the ground. Now we're not going to do anything sophisticated here, thinking in terms of one kind of energy leading to another. We're just going to do a simple particle calculation with the Suvat equations. So here we see for Suvat we'll need to use, we've got u is 0 when it's really, u equals 0, that's a u, v is what we're trying to find out, and the distance fallen is minus 10, and the acceleration will be just g, which is 9.8. If we take well, strictly speaking it's minus g, because if I write s is minus 10, I'm really taking positive upwards, so if I should have specified that first. If I take positive upwards, then s is minus 10, and this will be minus g, the acceleration. In which case, really to be consistent, I ought to show that. I think I'm going to leave it as it is, because it's g downwards, it's simply, it matches the arrow, and I'm going to have to make it minus g in the equation. So we'll get 2 times minus 9.8 times minus 10, and that really comes to the same thing if you take your positive direction as downwards, which is what I've done there. And the end result anyway, 2 times 9.8 times 10 is 196. That's the velocity squared. So the kinetic energy will be half times the mass, 5, times the velocity squared, 196, and that gives us 490. Now that means that the kinetic energy at the instant it hits the ground is 490 joules, and that means that since that was the answer for the loss of gravitational potential energy, we see a connection there, the two are the same. What's happened is that the potential energy that was, which is 490 if you take 0 for the ground, is released and becomes the 490 joules of kinetic energy as it hits the ground. So finally, the gravitational potential lost is equal to the kinetic energy gained. Our numbers show that, and these are both equal to the work done by gravity, because if we said what's the work done by gravity, it's the force, 5g, times the height, that's 10, which is exactly the calculation we did to work out to get the 490. So the work done by gravity is 490 joules too. Now this calculation anticipates the conservation of energy, because in a situation like this where there's only gravity acting, what's happening is that the potential energy is converted into kinetic energy. The one flows into the other, and the total of the two, as we shall see, will in general be constant. Well, that concludes this video presentation. The next in the same series on work, energy and power will be, as I've just said, conservation of energy. I hope to be with you later to explore that.